So let's see a particular class of signals, what are called as periodic signals. That means signals that repeat themselves after a certain time period, and an equivalent representation of that signal, what we call as time harmonic representation. A periodic signal, for example, let's say we are looking at in the time domain, that is the x-axis is the time. Then let's say there is a certain signal of some characteristics like this, and let's say beyond a certain time period t, which is denoted as capital T, this signal repeats itself. Yeah, it repeats itself. So turns out that if I choose any particular time instant t, if I were to choose another time instance which is capital T away, this particular signal, maybe let's call that V of t, the value of V of t is going to be same as the value of t plus value of the signal at the time instance t plus capital T. This value is essentially the same as this as well as this, whether we are choosing at this point or this particular point here. This t over here is the same as this t plus delta t value that we see here, which is essentially these 2 points. Not only that, the v of t is going to be equal to v of t minus t, and in general this is going to be equal to v plus nt, where n is going to be some integer, as long as n is some integer. So in general we can define a periodic signal to be having a time period of capital T, and that is going to be v of t plus capital T is going to be v of t. For such a signal, we can define what is called as the fundamental frequency, which is 1 over the time period. That means the time taken for one cycle of that periodic signal. The time taken for one cycle for that periodic signal is the capital T. The number of times the signal repeats in 1 second is going to be the fundamental frequency. The number of times it's going to repeat itself in 1 second, that is going to be the fundamental frequency, and that is 1 over the time period, and the units of course is hertz. And one full cycle of anything that is going in circle, that is periodically repeated, one full cycle is going to have 2 pi radians. So this frequency can be also written in what is called as an angular frequency, saying how many radians per second. This is how many cycles per second. This is cycles per second. And the same thing can be written in terms of angular frequency, which is the radians, the number of radians per second. And since one cycle has 2 pi radians, this is going to be 2 pi times that many cycles per second, which is 2 pi f naught, and it is going to be 2 pi upon t. And that unit is going to be radians per second, unlike hertz, which is cycles per second. So by the so-called Fourier series, we see that such a periodic signal v of t can be written in terms of sine and cosine trigonometric functions in as an infinite series having certain coefficients a0, an, and bn of the sort, and those coefficients multiplied by the cosine n omega naught t, where n varies from 1 all the way to infinity. This becomes the representation of the time domain signal. Now we notice that this particular term a0 does not depend with time. The coefficients an and bn are independent of time, and we have captured the time dependence in terms of the n omega naught, meaning it might be 2 pi f naught, omega naught is 2 pi f naught, 2 omega naught is going to be 4 pi f naught, and so on, all the way up to infinity, Now instead of having to write the long expression of sine and cosine all the time, a convenient way to write this entire expression is to switch to what is called as complex representation, where we are going to have the sine and cosines to be written in a more compact notation using or Euler's identity, which says e power j theta is cosine theta plus j sine theta. That is, e power j omega t is going to be simply cosine omega t plus j sine omega t. And by doing so, we see that the summation has to be from minus infinity to infinity, and we get a coefficient Vn, which now has to be a complex number and multiplied by e power j n omega t. Making use of this fact over here, in fact, we can show that this Vn is related to the An and the Bn as Vn is equal to An plus jBn upon 2, and V minus n is going to be An minus Jn upon 2, which in fact is the conjugate of the positive n. The coefficient for negative values of n, since this runs from negative infinity to positive infinity, n can be both positive and negative. The coefficients for the negative values is going to be the complex conjugate of the positive values. So in general, we see that this Vn is a complex number, and this complex number is what we call as a phasor, which we will see later. That phasor is a complex number. It has both a magnitude and an angle, and this a naught is what we call as that which does not depend with time, is like the DC term, and Vn is corresponding to the coefficient of the nth harmonic. This being the fundamental, the nth harmonic is, this is the second harmonic, fundamental is the first harmonic, the 2 omega naught t, the 2 times f naught is going to correspond to the second harmonic. So you have f naught, which is the fundamental, 2f naught is the second harmonic, and so on and so forth, all the way up to infinity. So in the frequency domain, you can see that if you were to plot the magnitude of this complex number, you can see that this is going to be a discrete set of values that extends all the way up to, from negative infinity all the way up to positive infinity, having a certain magnitude. But what is not also shown here is it has also a phase, which along with the magnitude, there will be a certain phase for each of those coefficients as well. But it is this a naught term which does not depend with frequency. It is at frequency equal to 0 is what is considered as the DC term, since it does not change with frequency.